Hello everyone. In the previous video, we have obtained these two relationships connecting the derivatives with respect to x and y to those derivatives, to those the derivatives with respect to s and n. And we are going to utilize these relations in the equation which we had obtained in the video previous to this, previous to the last one. So we are going to use these relationships back in the previous page. So that was in the video previous to the last one. So here, so what I'll do is I'll just copy this equation and start working on this utilizing the relations which I had obtained in the previous video. So let me go to the new page, paste it here, and I'll start working from here. So what I'll do is, first of all, I will collect the terms which have the del x terms common. So this term, I'll take this term together with this term, because both of them have the delta w del x, and I will consider this term together with this term. All right. I'll also make a couple of other modifications in the next step. Uh, I'll remove this subscript s from all these integration terms, which are basically cyclic integrals, cyclic line integrals over the entire contour of our domain. Because I'm going to use the s and n coordinate system variables, there might be a little bit of a confusion about which s is what, and so on. Furthermore, I will write this term which is not going to change through the subsequent steps first. So let me start today's work. I'll just write this as it is: d delta 4 w minus q delta w dA, and then this term, this mx nx plus this one mxy ny. Outside I have delta w del x, and the integration is with respect to s. Next, I will have, in a similar fashion, combining this term and this term, mxy nx plus my ny delta w del y ds. And finally, I'm going to take this term together with this term, plus qx nx plus qy ny delta w ds. This whole thing is equal to 0. Now the next thing that I need to do is to replace this del x term with what I had obtained in the previous video. So basically these relations. So obviously the terms are going to become slightly long, but no matter, we'll do the work. So I'll just copy this thing from here. I'll utilize that a little bit later. First, I'll just copy this term also together with up to here. And this del delta W del X term, that I'll just utilize from here. So all that I need to do is write this as minus ny del delta W del S plus nx del delta W del N. All right, I can erase this out. Next, I'll write this term. Sorry, I'll write this term and now I have to replace this del y term with what I had obtained in the previous video. So I'll again copy that out. Of course, I'll have to write the delta W terms. Okay. And then I'll have these terms which remain unchanged. Okay. Next, what I'll do is I really have to do uh, this expanding it out, but I'll do this. So the plan is like this. For the next step, I'm going to multiply all of this out. Okay, but at the same time, I will collect all the terms which have as their coefficient this del S term. Okay, so the del delta W del S term, that I will take as common, and similarly I'll take all the terms having del delta W del N as common. So I'm skipping a step here, but I hope it's all right. So uh, let me just write this down quickly. The first term remains as it is. So maybe it's a better idea if I don't do this here. Instead, I just copy this thing out and go to the next page. There's no point in cluttering it out. Okay. That remains the same. Next, I'll multiply this out. So that gives me minus mx, nx and y minus mxy and y squared. And I'll next consider these terms which have this del delta S term. So that is mxy nx squared with a minus, and then this term minus my. Of course, I have to be a little bit careful here. I already have a minus outside here, so I need to write this with a plus. So this is plus my nx and y. All right. I have that. Okay. I don't need the square bracket actually. Next, I'm going to consider the terms which will have the del delta n terms. So going here, what I'll have is mx and x square plus mxy and x and y from here, then plus mxy again nx and y. So this is basically a twice of that term, plus my and y square. Del delta w del n. Of course, I've missed this ts term over here, so I write that. And finally, this last term involving the q's, that remains unchanged. Okay. Now, so this is the part where I pull off a little bit of a stunt. Okay, the stunt is in this form, that this entire term, this entire thing, that I will write as another term of mns, and this entire thing within the first bracket, that I will write as mn, and I'll have a little discussion about it. But let me first write down what I want here. So please note that these are over the entire domains, over the entire domain. This thing that I'm writing as mns del delta w del s ds, and this entire thing that I'm writing as mn. Furthermore, this last term qxnx plus qyny, that I'm writing as qn delta w ds equal to 0. So what has gone on here? You see, let me just write that properly, that where I'm using mns is equal to so this is mx minus my. If you look carefully here, I'm taking nx and y common, plus mxy and x square minus ny square. Okay, and mn, that is just mx and x square plus mxy twice mxy and x and y. So I have combined this with this, plus my and y square. Okay, so what are these two relations? Why am I writing like that? So you see, even though these terms, this mx, mxy, my, they are the moments, but they are defined. If you remember, if you go back to the previous slides, you'll see that they are defined in terms of the stresses. So they are basically, this is coming from the sigma x, z dz integration from minus h by 2 to h by 2. Similarly, this is coming from the sigma yy term, and this mxy is coming from the sigma xy term. Now, all of these two relations that I have written, you can interpret that as coming from an equivalent relationship between the sigma ns and the sigma x, sigma y, and sigma xy, and here sigma nn with as it is connected to sigma xx, sigma yy, and sigma xy. And what are those two relationships? To sigma n and the sigma ns. So it may seem a little bit alien to you written in this particular form in terms of this n and s variable, very general mathematical looking, but I assure you that all of you who have undergone undergraduate mechanics of solids have actually come across these relationships, not in terms of these moments, but the relationships that I just alluded to, regarding the connections between the stresses that you have all come across in your undergraduate mechanics of solids. So you think about it a little bit. So if you remember what you did back when learning transformation of stresses in 2 dimensions, so you considered with respect to a xy coordinate system stresses like sigma xx, sigma yy, and sigma xy, and then you went on to obtain the relationship uh, for stress components in another rotated coordinate system, which was the x dash y dash coordinate system, and there you had sigma x dash, sigma y dash, and sigma x dash y dash, and you found out a relationship between those dashed variables, the dashed components of stresses, with the non-dashed components of stresses using the cos theta, sin theta, and so on. In fact, those were very important relationships as far as your objective questions were concerned. So you all know about that, and you can see that there is a direct connection between that if you just replace this nx by cos theta and this ny by sin theta. So that is why I'm saying that all of you are actually familiar with this thing. This is not something really new. Okay, so once you are convinced with this, but no matter, I mean, just to refresh your memory, I will give the these and this connection, establishing this connection again as a little exercise in the problem sheet associated with the classical plate theory. So that will be problem sheet number 3. So students who are enrolled in this Advanced Mechanics of Solids course will be able to do it and maybe ask their doubts during the live sessions. Anyway, so let me proceed here. What do we do after this? So you see, after we have obtained this, there is a little bit of thing that we can do to simplify this, especially with regards to this particular term, the term which is involving the del del s. So what I'll do is I'll copy this thing out. Go to the new page and focus my attention on this term involving this del del s. So what I want to say here is this. MNS del delta W del S ds. You see, this is a line integration. So if you are considering a contour in this fashion, if you're considering a contour in this fashion, you are actually, you may remember that uh, uh, we had considered our coordinate axis in this fashion. This was our x and this was our y, and our s and n were directed in this fashion, s n. So we were basically traversing this contour in this kind of tracking it like this. Okay, so if you go like that, what you're basically doing, you are starting out from a certain point. Okay, you're starting out from a certain point. Let that point be, let's say, some point p1. Okay, and you are going through the entire set of points which make up this contour, and then you are coming back to this point P1. So can we perhaps uh, think of doing an integration by parts for this? So what happens if we do that? So we proceed like we always proceed for integration by parts. We consider uh, this as our first bit and this as the second bit. So in this boundary term, it is this second bit which will be integrated with respect to s. So we'll obtain this delta w. So this is our boundary term. But please note that for this boundary, the lower limit is p1 and the upper limit is also p1, because this is a cyclic integral. Okay, and we are actually starting from a point and coming back after traversing the whole contour to the same point. That is why the lower limit is p1, the upper limit is also p1, which means that this boundary term, that is basically going to be 0, because no matter what the value of this mns delta w be, we do not know what it is, but whatever its value is at p1, it is the same value at p1, so we're basically subtracting the same thing from itself. Okay, so what will be left with is uh, this kind of a term. All right, so this is going to be 0. So this is going to be 0 for a closed contour. You understand that. So what happens if we substitute this back here? So we have the delta 4 w minus q, that remains unchanged. For this minus will become a plus courtesy this minus. This term remains as it is. And this term also remains as it is. Okay. So that I'll move that up a little bit. Please note that I have not explicitly discussed uh, this connection, this qn is equal to qxnx plus qyny, but just in the same way that we have obtained the connection between the sigma, the mn, the mns, and the mx, my, and mxy, we can obtain a similar kind of transform relation between the qn, qx, and qy, thinking in terms of the stresses. Okay. Now, where do we go from here? You please note that our ultimate objective, just like as it was back in beam theory, our ultimate objective here is to obtain a set of governing equations and the corresponding boundary conditions. So whatever simplification that we could have done, we have done here. So now it is time to finally write down the governing equations and boundary conditions. Well, after this long set of derivations, rather long set of derivations covering 5 parts of lectures, we can finally write down the governing equation here. As all that you have to do is pick out the term which is over the entire domain. Okay, so this is our domain term, and this, even though it is written in terms of an integration here and integration here, but these are integrations over the boundaries. Okay, boundary means over this periphery. Okay, so For the governing differential equation, we only need to worry about this or consider that it's like this. And please, I request all of you to please make a comparison of this equation that we have obtained for the classical plate theory with the equation that we had obtained back while considering only the bending of beam much earlier. Okay, so there also we had obtained an equation which was like EI d4w dx4 is equal to Q. So you make a comparison with this equation with that equation. Okay, so they are both fourth order equations. The difference is that here we have this D term, which is the bending rigidity, and back there we had the EI term, which was like the flexural rigidity, and this Q of course is the same thing. There we had just the 1/4 order derivative term with respect to x, because that was a one-dimensional problem. But this is effectively this classical plate theory has enabled us to reduce the whole problem to effectively a two-dimensional theory, even though we started out by considering a three-dimensional problem. But by integrating out with respect to the z direction, we have effectively reduced this to a two-dimensional problem, and this del 4, the biharmonic operator, that takes into account all the derivatives with respect to x and y. Next, for the boundary conditions, I have either, so I'm going to consider this term now, either del mns del s together with this term, because you see that this has the coefficient of delta w, this also has the coefficient of delta w, that is equal to 0 or w is specified. Next, we consider this term and say that either mn is equal to 0 or del w del n is specified. So there is a lot of similarity with what we had obtained back in beam theory with what we are obtaining here. So just to mention the physical interpretation of this, you see that if for example our plate is clamped, then we would know that along the entire periphery the w would be 0, but more importantly w would be specified. So for a clamp plate we would have to consider this and reject this. Similarly, if again our slope is given, for example, again if the plate is clamped, then we know that the del w del n that would be 0, so we have to reject this term. But if on the other hand our plate is simply supported, then we have to consider this mn equal to 0, which represents the moment. So a simply supported plate would not have any resistance to rotation, and that would be given by this condition, the 0 moment condition, all throughout the periphery. And suppose a certain portion of the periphery, that is not clamped, not simply supported or anything, it is just free, then you understand that the condition, the physical condition there would be that it is having 0 shear, and it is this condition, okay, the 0 shear condition is present by that. And of course you will have the appropriate condition from this statement also. Okay, in fact you will have this mn equal to 0, because a shear because a free part of this periphery would not have any slope specified there, so it is this condition which would again be applicable. So depending on the kind of problem that we are handling, we'd have to choose the appropriate boundary conditions. Now, this particular thing that we have obtained here, that has a certain special discussion associated with it, but we'll see about it later. So for now, I'll stop this video, but as far as problems are concerned, what we'll do is we will take up problems, a number of problems uh, uh, considering a circular plate. Now, when we have to specialize to the case of a circular plate from this general NS coordinate system, what we have to do basically is to go from this NS to a R theta coordinate system. Okay, so that entails another set of transformations, but those are some things which are quite familiar to you, at least if you directly think in terms of going from the xy coordinate system to the r theta coordinate system. You know how to do those transformations courtesy what we learned during applied elasticity, but at the same time it is still possible to go directly from this ns coordinate system to the r theta coordinate system, but we'll see about that later. So that's all for now. Thank you very much.